exponential growth and decay functions. Exponential growth parent functions. So growth, ab to the x, happens when your b value, your rate, which is called the growth factor, is greater than 1. So what happens is if you look at the graph, it increases as you move from left to right. Now, these exponential functions have an asymptote at y equals 0. That means that that's a boundary that this graph is not going to cross. So right here at y equals 0 on the x-axis, there is an imaginary boundary line. That means that my function will never reach negative y values. Then, exponential decay, y equals ab to the x, is when your b value is between 0 and 1. Basically, it's smaller than 1, but not negative. We call this a decay factor this time because it's an exponential decay. That means from left to right, your graph is decreasing. Your y values are going down when you move left to right on the graph. Just like the exponential growth function, this also has an asymptote at y equals 0, which means the exponential decay function will never reach negative y values either. So let's talk about graphing these exponential functions. There's a few steps. So identify the value of the base. This will tell you if you have exponential growth or decay. So if you are increasing from left to right or decreasing from left to right. Then make a table of values. So the domain is all real numbers. That means I can have any x I want, but I need to be sure to include negative and some positive x values. Once I have my table, plot the points. Then step forward, draw the graph from left to right, but don't forget about the horizontal asymptote at y equals 0, meaning we're not going to go underneath the x-axis. So example 1, tell whether the function below represents exponential growth or exponential decay, then graph the function. So we have y equals ab to the x. Well, the b value is a 2, and 2 is greater than 1, so that means we actually have exponential growth. So that means our graph will be increasing from left to right. So since we're increasing from left to right, I want more positive values than negatives as far as the x's go. So I only have 2 negatives and I got more positives because that's where the majority of my graph is going to be. So now that we know what our domain is going to be, we need to figure out our range. We need to find those y values. So we're going to take each x and substitute. So the first one is y equals 2 to the negative 2 power. Use some kind of calculator to help you with this, and that's going to give you 0.25. So that's the first value in my table. Then we're going to take 2 to the negative 1, which is going to equal 0.5. That's our second value. Then we want 2 to the 0, which is a 1. Then we want 2 to the first, which is 2. 2 squared, which is 4. And then 2 to the third, which is 8. So now that we have a pretty good value of tables, we're going to plot these values on our graph. Make sure you're looking at the scales that we're given. So our x's are going by 1s and our y's are also going by 1s. 1, 2, 3, 4. So when we plot these values, negative 2, negative 0.25 is going to be close to my axis. Negative 1 half, 0, 1, 1, 2, 2, 4, and 3, 8. When we connect this, remember we need to not forget about our boundary line, our asymptote at y equals 0. So our graph gets really close to the axis from left to right and then increases, moving left and right forever. And there's the graph of y equals 2 to the x. Example 2. Tell whether the function below represents exponential growth or exponential decay, then graph the function. So again, our general layout is y equals ab to the x. So b is that 1/2. So we have 1/2, which is smaller than 1. So in this case, we have exponential decay, which means our graph is going to be decreasing from left to right. Now I don't have the x values pre-filled in this time. So since these are moving from left to right and it's decreasing, that means your higher y values are on the negative end of your x. So I want more negatives than I do positives. Now that I've chosen my x values, we're going to find the y values by substituting. So y equals 1/2 to the negative 3, which is going to give us 8. Y equals 1/2 to the negative 2, which is going to give us 4. If you notice, this is just the opposite of the other table. That's not always the case, though. If I had done something like maybe 1/3 to the x, that's going to give us a different values. Y equals 1/2 to the 0 is a 1. Y equals 1/2 to the first is 1/2, or we're going to think of it as 0.5 because sometimes decimals are easier. And 1/2 squared is 0.25. Now that we have our values, let's go plot them on our grid. So we have -3, 8, -2, 4, -1, 2, 0, 1, 1.5, and 2.25. And we also can't forget about our horizontal asymptote at y equals 0. So when we graph this one, we're going to decline from left to right, but we're not going to cross the x-axis. We're just going to get very close to it. And there's the graph for y equals 1/2 to the x. Exponential models for real-world applications. So we use an exponential model when these real-world applications increase or decrease by a fixed percent each year or some other time period. So there's two models we use. We use an exponential growth model, is if we have a percent increase, which of course we write as a decimal. The equation for that is y equals a, which is the initial, times 1 plus r to the t, and r is your rate. Then the exponential decay model is exactly the same, but it's 1 minus r instead. So if you're increasing, we're going to do 1 plus r. If you are decreasing, we do 1 minus r. And again, a is the initial, and r is the percent decrease written as a decimal.
Example 3. The value of a car Y in thousands of dollars can be approximated by the model Y equals 25 times 0.85 to the t, where t is the number of years since the car was new. So letter A says, is this situation exponential growth or decay? So we need to look at B, which is here in the middle, and we need to decide, is that greater than 1 or less than 1? And since B is smaller than 1, 0.85 is less than 1, we have an exponential decay situation going on. So letter B, identify the annual percent increase or decrease in the value of the car. Well, first of all, it is going to be a percent decrease because we know we have decay. So to identify the annual percent increase, we're really looking for R, which kind of is built into this 0.85 thing. So on the basic layout of our function, we had A equals 1 minus R to the t. And so this is what the percent increase or decrease is, not necessarily the entire number on the inside. So we need to figure out what value of R gave me an inside value of 0.85. So you can either think through this logically, or you can solve for R. Subtract 1 from both sides, and we end up with negative R is equal to 0.85 minus 1 is a negative 0.15. And then divide out negative 1 to have an R value of 0.15, which gives us a 15% decrease per year. Letter C, estimate when the value of the car will be $8,000. So we do know that they are in fact giving us the value of Y because we're talking about money. The thing is, though, if I look back up at the top, it said the value of the car Y in thousands of dollars. So Y was in thousands of dollars. So that means Y is not really 8,000. My Y is really simply just 8. So if I look at my equation with 8 substituted, we have 8 equals 25 times 0.85 to the t. Well, if I want the value of t, I have to solve this equation for an exponent, which I don't really know how to do yet. So we're actually going to use our graph and our table in order to find the answer to this question. So let's go ahead and graph this function in our TI 84. So y equals, let's clear out what I have from a previous problem, and let's graph this problem. So we have y equals, let's do it in y1. So 25 parenthesis 0.85 parenthesis, to the value of x. And I realize I have too many decimal points here, so I'm going to have to go back, highlight over 1, and I'm going to delete. And we press enter and graph. And so here's our picture. So I'm actually going to use the table feature to find the value of t when the value of the car, the y, is about 8. So I'm going to do second and then graph to get my table. And I want to know, where is my y value about 8? So here's 9.4, 8.01. It's probably about as close as we're going to get, because if I move down a little bit more, I'm way past a value of 8. And so it took about 7 years, to get to a value of $8,000. So please be sure you're paying attention to units very carefully. Let's look at example 4. In 2000, the world population increased by about 6.09 billion. During the next 13 years, the world population would increase about 1.18% each year. So letter A is write an exponential model giving the population y in billions t years after 2000. So I have to come up with the equation myself this time. Well, first thing we need to figure out is, are we doing exponential growth or exponential decay? So if I find my rate, here's the rate, and it tells me that we are increasing at about 1.18%. So that increase means we actually have exponential growth. So the layout that we are going to be using is a times 1 plus r to the t. Well, y is just y. A is the initial amount for this problem, which it said in 2000, the population was 6.09 billion. We're going to do 1 plus because it is an exponential growth, and the rate is 1.18%. We can never use a percent as a percent. We have to change that percent over to a decimal. So we take the current decimal place and move it 2 times to the left to make it into a decimal. So it's really 0.0118 that we are working with. So all we need to do now is simplify this inside. So we have y equals 6.09 times 1.0118, because that's what happens when you add these two together, to the power of t. So here is the model that represents this situation. So letter B, estimate the population in 2005. So I don't know the population, that's why it's asking me to estimate it. That's the unknown. What I do know is that the value of t is in 2005. Well, again, be careful with units. It actually says that t is the number of years after 2000. So t is not 2005, t is simply 5, because 2005 is 5 years after the year 2000. So if we plug this in, let's see what we have. We have y equals, that's the population that I don't know, 6.09 times 1.0118 to the 5th power. And if I look at this equation versus the last equation I had, my variable is all by itself already. So we're not solving here, we're really just simplifying this right-hand side. So we can use our calculator for this and just get a basic value. So I'm going to pull up the calculator. I'm actually going to quit, so I'm going to do second, quit, and let's type this guy in exactly as it shows, and let's get a calculated value. So 6.09 parenthesis 1.0118 close parenthesis to the 5th power. And let's see what we get. We get a y value of about 6.457. So if I want to round to 2 decimal places, just like it gave me in the initial, this would have to be 6.56. So in 2005, the population is about 6.56. Let me make sure it's a 5.6 or 4.6. Let's see. 6.46. So 6.46 billion people. Remember, it's not just 6 people, it's 6.46 billion people. Letter C, estimate the year when the world population was 7 billion. So this is very similar to the question we had earlier. Estimate the year means I don't know the t. Estimate the year, I don't know time, but I do know that the population was 7 billion. So if I plug in my 7 equals 6.09 times 1.0118 to the t. This is, again, our variable that I don't know how to solve for yet, so we need to graph in order to figure this one out. So let's use y equals, let's clear out what y1 is, and let's type in what we have. So let's ignore the 7. We're going to deal with that in a minute. So 6.09 parenthesis 1.0118 to the x, or t. It automatically changes it to an x. Sorry, my little thing messed up. Go all the way to the right. There we go. To the x. And now we graph. And we need our table because I want to know when is the population 7 billion. So second graph. So I need to find a y value of a close to 7, as close to 7 as I can get. So it's 9 is at 6.7. An x value of 10 is 6.8, 6.9. There's 7.01. And if I go up, I'm getting further away from 7. So this is the closest to 7 that I can get. So that means t has to be 12, but it's not year 12. Remember, t is the number of years since 2000. So the year that the population was 7 billion is actually in the year 2012.
Now let's talk about some compounded interest. So this happens with usually like bank accounts. So consider the initial principal P. So what that means is that's the initial amount. So this P is the initial amount deposited into the bank account that pays an interest at an annual rate R expressed as a decimal. So R is the interest rate that is compounded n times per year. So this n is how many times a year you're being compounded. Compounded per year. So let's talk about that for just a minute. So if you are compounded, let's say yearly, well, how many years are in a year? Well, that would be 1. So your n would be a 1. If you were compounded daily, how many days are in a year? 365. So that would be your n. Let's say you're compounded weekly. Well, how many weeks are in a year? That'd be your n of 52. If we say we are compounded quarterly, well, if we divide a year into quarters, that means your n would be a 4. And then the last one that's most common is monthly. If you're compounded monthly, that means you have an n value of 12. It's basically how many of those increments can you fit into a year. That's how you can figure out what n is. And then it says the amount A in the account after t years. So A is actually your final amount. That's usually what we're looking for. And t is the number of years you're doing this for. So maybe I want to leave the money in the account for 2 years, 8 years, half a year, however long we want to leave the money in the account. So let's talk about an example. You deposit $9,000 into an account that pays 1.4% annual interest. Find the balance after 3 years when the interest is compounded quarterly. So first, let's find all of our pieces. So it says you deposit $9,000 into account. That means that principal, the initial, is $9,000. Then it pays 1.46% annual interest. That's that R. But we can't use 1.46%. We need to change that percent to a decimal. So move the decimal point 2 times to the left. So R is actually 0.0146. Now it says find the balance after 3 years, so that will eventually be T, when the interest is compounded quarterly. So compounding quarterly means your n is going to be a 4. So let's write down the original equation. A equals P times 1 plus R over n to the T. So let's write the general equation first, then we'll figure out the balance after 3 years. So the general equation, the P is going to be the $9,000 that you originally put in the account, 1 plus the R as a decimal, the rate was 0.0146. The n is compounded quarterly, so it's a 4, and then to the t. So this is the general equation that you can use for this account after so many years. So I can plug in different values of t and find out the amount that comes out. Well, it wants a specific of 3 years. How much money will be in this account after 3 years? So now we're going to take this equation and substitute in a 3 for t. And we're going to evaluate. So use your order of operations to make sure you evaluate this in the right order. So I need to get this inside the parentheses stuff as simple as possible. So I'm going to do first the 0.0146 divided by 4. So 0.0146 divided by 4 is about 0.00365. Then I need to add 1 plus 0.00365, which is just 1.00365. Now I can use the exponent. So I'm going to take 1.00365 to the third power. So we get 9,000 times 1.012. And then finally I can multiply these together. So 9,000 times 1.012 is 9,098.91. So this is the amount of money in the account after 3 years with this interest rate and compounded quarterly.